so that the sphere rolls without slipping. So now here, what is the minimum value of mu? So first of all, we have to understand for a body to roll, it requires friction. If at all that friction is not maintained, it will be a sliding body only. It becomes a sliding body only. So that's why it requires friction. Now the question is, what is the minimum value of mu so that it can roll along that inclined plane? So for that we are taking, that is a free body diagram. What are the forces that are acting on this rolling body? And generally first we derive that general formula. We derive that general formula for any rolling body, and we can apply that general formula for any object, for any rolling body. That may be the sphere or the hollow cylinder or the solid cylinder or the hollow sphere or the circular ring or the circular disc, anything. So first it is this is the analysis of forces. So first it is mg is here, and this can be taken as mg cos theta. So this the theta is here, and this will be normal reaction. So this is a normal reaction, and thereafter it is mg sin theta. Mg sin theta is here, and there it is the frictional force is here. So that can be taken Fk. Mg sin theta, and again this is the first of all mg is here, that acts vertically downwards towards the center of earth, and mg cos theta and a normal reaction, and mg sin theta, and frictional force that opposes the rolling of this body, movement of this body. In this case, so that resultant motion is ma. That resultant motion is ma. And here net force is equal. So it is a net force is equal to, in this case first of all what you have to take, it is the mg sin theta minus frictional force. Net force is equal to mg sin theta minus frictional force. So that's why net force is equal to ma, and that will be mg sin theta minus f is here, and that is taken as the first equation. And here our target is to find out the mu value. As I already told you here, definitely that a friction is needed for the body to roll. So that's why what is the minimum value of the mu, so that the body can roll now without slipping, without sliding. So in this case it is mg sin theta minus f, that is the equation is there. Now we are taking, for the body to roll there must be some force. So here that is the torque is equal to F into R is the formula, and the torque is equal to I alpha is the formula, and when you are combining them, that is F into R is equal to I alpha. F into R is equal to I alpha. Because of the friction only the body is rotating. The friction acts as a force which rotates this body. So that's why force into perpendicular distance, F into R is equal to I alpha. Now when you are coming to this, F is here and R, I can be taken as mk square is the general formula, and here that is the alpha. Alpha can be taken here in this case A by R. Alpha is equal to A by R is here. So now here it is F is equal to mk square by A by R square is here, and when you are taking that, suppose ma, because we can remove this ma. Why? Because our requirement is the F. So that's why we remove this ma. Ma is equal to, we eliminate this ma is equal to Fr square by K square is here. This is second equation. ma is equal to Fr square by K square is the second equation. Now from 1 and 2, what you can have, it is ma. In place of the ma, what we can write, it is the Fr square by K square. So Fr square by K square is equal to mg sin theta minus f is here. Fr square by K square is equal to mg sin theta minus f. And from that, if f is taken common, that becomes 1 plus r square by K square, and it is mg sin theta. And thereafter f is equal to mg sin theta by 1 plus r square by K square. 1 plus r square by K square, mg sin theta by 1 plus r square by K square. And thereafter already you know f is nothing but mu r, and it is nothing but mu mg cos theta. So that's why in place of the f, what we can write, it is a mu and a normal reaction. In place of the normal reaction, mg cos theta will come. So that's why it is a mu mg cos theta is equal to mg sin theta by 1 plus r square by K square is here. And thereafter it is a mu is equal to tan theta by 1 plus r square by K square. mu is equal to tan theta by 1 plus r square by k square, and this is the minimum coefficient of friction, that is mu minimum is equal to tan theta by 1 plus r square by k square. And here this is the general formula, we can apply this general formula for any rolling body. Suppose in this particular example you are given it is a solid sphere. For the solid sphere, what is that k square by r square? It is 2 by 5. So for the solid sphere it is a 2 by 5. Therefore, mu minimum for that sphere. So for sphere, unless otherwise mentioned, you always have to take a sphere is nothing but the solid sphere only. If at all it is the Hurler sphere, it will be specially mentioned. Otherwise, you have to take it as a solid sphere. So for sphere, mu minimum is equal to tan theta. Here that theta is given, you are not given any value for that theta. So that's why you have to take a tan theta only. And 1 plus, and just now I told it is a k square by r square is the 2 by 5. So r square by k square is becoming the 5 by 2. So 5 by 2 is here. So it becomes a 7 by 2. So now it becomes a 2 by 7 tan theta. That's all. Mu minimum in this case is 2 by 7 tan theta for the sphere. This is the minimum coefficient of friction. So once again I tell you. So first of all, you are given, this is the information that you are given, that body is rolling, that sphere is rolling along this inclined plane, and in this case, it is a net force is equal to mg sin theta minus f. Mg sin theta minus f is here, ma is equal to mg sin theta minus f, that is the net force. And thereafter, torque is equal to f into r, and again the torque is equal to I alpha. And Fr is equal to I alpha, and from that ma is equal to, because first of all, your target must be to find out the f value. That's why you have to eliminate this ma. So ma is equal to fr square by k square is that second equation. From 1 and 2, you are having that ma can be replaced by fr square by k square, and f of 1 plus r square by k square is this much. You are getting this answer. This is the general formula. Mu minimum is equal to tan theta by 1 plus r square by k square is the general formula. And if you are applying that general formula for this present case, if that is for the solid sphere, you are getting this answer. Mu minimum is equal to 2 by 7 tan theta. That's all. Now we can go to the second problem. So for that second problem, a mass m is moving with a constant velocity. So a mass m is moving with a constant velocity along x-axis and parallel to x-axis, and now what is its angular momentum with respect to origin? So that's why here a mass m is moving, that is parallel to x-axis with a constant velocity. Now here we are taking, this is the particle is there and it is moving parallel to that x-axis. So that's why it is a x-axis can be written, and thereafter it is a y-axis, and it is moved with a constant velocity, means definitely it will have the constant momentum also. So that's why p is here, it is a constant. Now you are supposed to find out what is its angular momentum, and there you are given three options. One is that angular momentum increases. When you are finding that angular momentum with respect to origin, it increases, and thereafter it decreases, and the last option is remains unchanged. So now here we are taking that with respect to origin means it will be like this. With respect to origin, it will be like this. And you may get confused. Now it is the L is equal to P into R. L is equal to P into R. So that's why P is a constant and R is increasing. That's why you may get confused. That's why L is equal to increasing. But it is not correct, because L is equal to P into R is applicable only when that theta is 90 degrees. That is P and R are mutually normal. When that P and R are mutually normal. So, but here the general formula is L bar is equal to R bar cross P bar. R bar cross P bar, and that indicates L is equal to P R sin theta. So, this is the general formula, P R sin theta. And here P is always constant, because mass is constant, and you are given that a problem that velocity is also constant. So that's why P is constant. The problem is here with this one only, that is with this R sin theta. So P is constant. Here just we describe that moment of this body, and here this is the R1 is here, and this becomes the theta 1, and here that is the P bar is there. R1 bar is here, and this is the P bar is here. So the angle between this R1 bar and the P bar is the theta 1. And similarly, this is taken, this is the theta 2, and similarly it can be taken theta 3. So it is R2 bar, and again the R3 bar, and from that what we can conclude, it is R sin theta, R1 sin theta 1, R1 sin theta 1 is equal to R2 sin theta 2 is equal to R3 sin theta 3 and remains, that is a constant. That is a constant. R1 sin theta 1 is equal to R2 sin theta 2 is equal to R3 sin theta 3, that remains a constant. So first L bar is equal to R bar cross P bar, and L is equal to P of R sin theta and R1 sin theta 1. Here R1 is increasing, at the same time theta 1 is, that is theta is decreasing, and the product of that R and sin theta, the product of that R and sin theta remains unchanged, that will be maintained constants. Now what is the conclusion? Here P is already constant and R sin theta is also constant, that's why that angular momentum remains unchanged. So that is the point here. So angular momentum remains unchanged. Next one when you are coming to the third problem here, so here it is a second problem, just it is based on concept only. So it is the description of a clear description of that angular momentum definition. Now it is, we are coming to this third problem. A circular disk is rotating about its natural axis with an angular velocity of 10 radian per second, and a second disk of same mass is joined to it coaxially. So now here it is just based on the conservation of angular momentum. As I already explained in that theory, that is a conservation of angular momentum, that is I1 omega 1 is equal to I2 omega 2. Here also we are taking this disk is here. So this disk is here. So in this case, in this disk, it is to a circular disk is rotating about its natural axis. Natural axis means, that's why it is the passing through that center and perpendicular to the plane of that disk. Plane of that disk, now it is to rotate like this. In this case, when it is rotating, and it is rotating with a velocity of 10 radians per second, and a second disk of the same mass is joined to it coaxially, if the radius of the disk is half of the radius of the first one. So that's why we are taking the second disk is also here. So initially what we are taking, it is the M, and here also it is the M, because there is no any change in the mass of that second disk also. It is containing that same mass, it is having that same mass, but the radius is, in this case, so initially it was that radius is the R, and here in this case it is R by 2 only. It is R by 2 only. In the first one, it is rotating with an angular velocity of 10 radians per second. Now, when this second disk is arranged coaxially like this, and what will be that new angular velocity? And here definitely we can apply that conservation of angular momentum, because there is no any external torque acting on it. When there is no external torque acting on it, we can apply that formula I1 omega 1 is equal to I2 omega 2. I1 omega 1 is equal to I2 omega 2. So here the I1 first. I1 is equal to, when there is no that second disk. So in that case, I1 is equal to, for the circular disk, as you already know about that natural axis formula, it is mr square by 2. So that's why it is mr square by 2 to be taken, mr1 square by 2, and omega 1 already you are given, that is a 10 radians per second. You are already mentioned that a problem, it is a 10 radians per second. And I2 means here the two objects are having a common angular velocity, that is the first disk and again the second disk. So that's why you have to find out that moment of inertia, so separately for them. That is for the first one, as you already know, it is mr1 square by 2, and for that second disk it is m is here, and it will be r2 square by 2, and that is r2 square by 2. Now here they are having that common angular velocity omega dash. They are having that common angular velocity omega dash. So in this case, so first of all, mr square, let r1 is equal to r1 kundam. So mr1 square is the mr1 square by 2 is here, and it can be 5 is here. So after that multiplication, after that cancellation, it becomes the 5 only. Next here mr1 square by 2, mr1 square by 2, and m, and here r2 is equal to r1 by 2 whole square. So r1 square by 4 into 2, that becomes 8, and here it is omega dash. So once again I tell you, now it is mr1 square by 2, and again here it is the 10. So after that multiplication, it becomes a 5 only, and here it is mr1 square by 2 plus m, R2 is equal to, already you are given it is half of the radius, so that's why R2 is equal to R1 by 2 whole square, R1 square by 4 into 2, that becomes 8, and again omega dash is there, and thereafter it is m R1 square by 2 plus, so when you are taking that LCM, it becomes 8, and it is the 4 times, and it is 1, so 5 m R1 square, and as usual it is the omega dash, and m R1 square into 5 is here, that 5 will be cancelled, and m R1 square also will be cancelled. So omega dash is equal to 8 radians per second. This is a common angular velocity. This is a common angular velocity. With that velocity, with that common angular velocity, these two disks rotate together. These two disks rotate together. Omega dash is equal to 8 radians per second. That's all. Next, so this is a simple application of the conservation of angular momentum. Now we are coming to that fourth problem.